Hello friends, we are back with our MOOCs course on fundamentals of nuclear power generation. And this is or at the present we are almost at the halfway stage of this course, because we have gone through 6 weeks and 6 more to go. But the 6 modules that we have finished, actually in content wise we have already covered more than half of the course, because the topics that we have covered in the previous 6 modules, they are more heavy, involves quite a bit of mathematics and concepts, etc. And that is why that has taken more number of lectures than what the next 6 are supposed to take. But the topics that we are going to discuss from today onwards, they are probably more important from practical point of view, because here we shall be talking more about the external fields or external factors which are known to any common people. And that will be starting with this particular module in module 7, where we shall be talking about thermal reactors. In previous 6 modules, if I would like to have a quick recap of that, in the first module you have learned about the very basics of nuclear energy production, particularly through the concept of binding energy and mass defect. In the second module you are introduced to the topic of radioactivity. Particularly in the topic of artificial radioactivity, you have learned that by striking the nucleus with a suitably charged particle, we can induce radioactive decay even in a stable isotope also, or stable nucleus. But the nature of such nucleus, or I should say the outcome of such an interaction between a neutron and nucleus, that will depend upon both the energy level of the neutron and also the nature of the nucleus. And from there we got the concept of nuclear cross section. Only a few certain nuclei can have fission cross section of any significance, and in the third module we have discussed about those isotopes or those nucleus, and also more detailed about fission. In the fourth module we talked about the neutron flux profile, because generally the energy released during fission reaction is directly proportional to the neutron flux, and therefore, we have discussed about the profile of neutron flux that we can get in different kinds of idealized reactors in order to sustain a critical reaction, or I should say in a critical reactor, what should be the neutron flux profile that we have seen there. In the module number 5, we actually came out of the reactor a bit, or I should say came out of the neutronic interaction part, where we discussed about the thermal hydraulics, that is the energy which is produced during the fission reaction, how that can get transferred to the coolant, that we have learned in the 5th module. In the 6th module, we again discussed about the control issues, particularly in our transient operation, because some planned transients or some unplanned transients, how to control that kind of issues that we have discussed in the 6th module, where you have learned the terms like important component of nuclear reactors such as the control rods, chemical shields, etc. And also we have discussed about the role of various parameters such as the delayed neutrons, fuel burn up, temperature, etc. So, now we know that in any reactor generally we have 4 different substances. Number 1 is the fuel. A fuel is the one which goes through the fission reaction, thereby produces a large amount of energy by virtue of its own radioactive decay or nuclear decomposition. Commonly uranium 235 nucleus is the fuel that is used, but uranium 233 or plutonium 239 can also be used as fuel. Second substance is moderator. Moderator is the one which allows the neutron to go through multiple scattering, thereby converting the prompt neutrons to the thermal neutron level, or high energy fast neutrons released from a fission reaction gets converted to the thermal neutron level by repeated scattering or repeated collision with the moderator nucleus. And that is very important, because the conventional fuels like uranium 235 or plutonium 239 has much higher neutron fission cross section when they are subjected to thermal neutrons. That is why moderator plays a very important role in increasing the power output from a reactor. The third substance is coolant. The energy which is released by fission, that needs to be transferred to the coolant, which actually will be interacting with the external world, and the net output from the reactor generally be manifested in the form of energy rise or energy gained by the coolant itself. And number 4, just we have studied in the previous module, the control rods or control electric equipments. Control rods are universally present in any kind of reactor. Certain other reactors can also have chemical shim or burnable absorbers, but they generally all use similar kind of materials like boron or cadmium or hafnium or gadolinium, which has very high neutron absorbing cross sections. So, we commonly can have 4 types of elements, it is fuel, moderator, coolant, and also the control equipments. And we can also have certain things like the fission products, the neutron poisons, etc., that are generally only a byproduct of the fission reaction. So, do not need to be considered at the moment. But the 4 that we have mentioned, depending upon their combination and also their orientation, we can have different kinds of reactors, and that is precisely what we are going to discuss in this lecture. Now, nuclear reactors can be broadly classified into 2 categories depending upon what kind of neutrons they use. When they use fast neutrons, we call them fast neutron reactors. When they use thermal neutrons, we call them thermal neutron reactors. And thermal neutron reactors are the most common one. More than 90% of the reactors, maybe more than 95% of the reactors which are available commercially throughout the world are actually thermal neutron reactors, because of certain reasons which we shall be discussing later on. Thermal neutron reactors again can be classified depending upon what kind of moderator they are using. Like 3 principal kind of moderators which are used in thermal neutron reactors are common water, heavy water, and also graphite. Here in the slide the term light water is mentioned. I probably have mentioned earlier also that the term light water is frequently used in the nuclear field. However, it is not a proper term, because this is just the ordinary water that we are talking about. There is of course heavy water, but there is nothing called light water. Still, this being such a common terminology in the nuclear field, we have to keep on using this. So, we can have depending upon moderator, we can have 3 types of thermal neutron reactors: the ordinary water reactor or the light water reactor, heavy water reactor which uses D2O as the moderator, and of course, the graphite moderator reactor. And the light water moderated reactor again can be classified into 2 categories depending upon the physical state of the coolant that they use. It can be pressurized water reactor where the coolant remains under single phase because of high system pressure, or the coolant can undergo a phase change, then we call that a boiling water reactor. The graphite moderated reactor again can be of 2 types. One which uses some kind of gas like carbon dioxide or helium as the coolant, other which uses water as the coolant. The fast neutron reactors, by definition it needs to use the fast neutron. So, there is no moderator there, and it generally uses liquid metal as the coolant. This is a typical neutron flask profile, and for the thermal neutrons reactor, the thermal neutron reactor generally operates in this zone, where the neutron energy is of the level of 0.025 electron volt, whereas the fast neutron reactors operate mostly in this particular zone, where the neutron energy is very high of the level of 1 MeV or can be even higher. These are the most common or conventional nuclear reactors that we can find throughout the world. As mentioned here, we can have generally 6 types, I should say: pressurized water reactor or PWR, boiling water reactor or BWR, then pressurized heavy water reactor, gas cooled reactor, light water graphite reactor, and also the fast neutron reactors. Out of this, all these 5, they are actually thermal neutron reactors, because they use thermal neutrons to induce the fission reaction, but the last one, that is a fast neutron reactor, that uses fast neutrons for the to induce the reaction. And we can also see in the first 2, that is PWR and BWR, water acts as both moderator and coolant, whereas in case of pressurized heavy water reactor, heavy water is used as both moderator and coolant. In case of gas cooled reactor, the moderator is graphite and coolant is a gaseous material like carbon dioxide. and in light water graphite reactor the coolant is water, but the moderator remains graphite. Now, the first one, probably the most common one, that is a pressurized water reactor or PWR. Pressurized water reactor is the most common type of nuclear reactor that you can find throughout the world in different countries, like in United States, in several European countries like Germany or France, and also in several other parts of the world. Actually, in India, the first nuclear plant that was established at Tarapur, Maharashtra, that reactors were also of PWR category. In case of a pressurized water reactor, the main component is a pressure vessel. This pressure vessel, generally made of steel, is the one inside which all the fission reaction happens. Inside the pressure vessel, we may have the fuel elements, which can be of the shape of cylindrical rods or maybe rectangular pellets. They are placed following certain kind of orientation, and control rods, the control rod material is generally boron or some compound of boron like boron carbide or boron oxide, which are allowed to pass through the gap between these fuel elements, so that they can capture some certain portion of neutrons available there depending upon their level of insertion. It was mentioned in the previous lecture also, a previous module, that in PWR the control rods are inserted from the top, and hence the control rod connecting mechanism or driving mechanism, particularly the spider, that is mounted at the top of this pressure vessel. And these fuel elements and also the control rod, they are completely immersed into the moderator, and the moderator in this case is water, that is only liquid water. No phase change is allowed in pressurized water reactor, and the water, that is as coolant and moderator that we are using, that must remain as single phase liquid in order to operate a pressurized water reactor. So, if we follow the diagram, the liquid, generally cold water, that enters the reactor through a channel like this. Inside the channel, it passes through this line and then is allowed to move upwards through the fuel or through the spacing between two neighboring fuel rods or fuel pins, and therefore, it is able to capture the energy that is released by the fission of the neighboring fuel particles or fuel isotopes. So, when it comes out of this fuel bundle, then this same water is at a reasonably high energy level, and if we can maintain the water under liquid condition, then definitely its temperature will be much higher than the inlet temperature. The water comes out of the reactor here, and so between this point, which we can mark as 1, which is the inlet for this water, and this is the 2, which is the outlet of the water. Between these 2 points, there will be significant difference in the energy level or enthalpy of this water, but physically both of them will remain as liquid. Now, the component which ensures this liquid status is this pressurizer. We shall be talking about pressurizer afterwards, but this liquid water then is allowed to come to a steam generator. Inside the steam, this liquid water, high temperature liquid water I should say, travels through a heat exchanging pins or heat exchanging arrays. Outside of that, again water is flowing, but that water is not allowed to mix with the water that is coming from the reactor itself. Rather, the water coming from the reactor is at a high energy level or high temperature, and therefore, it is able to transfer the energy to the water which is outside, which actually is the coolant, and then this water goes back to the reactor. Therefore, we can clearly say that in case of pressurized water reactor, we are using water as the moderator, as the coolant, and also as the working fluid. The steam which is produced in this steam generator, this one, that is allowed to go through a turbine where it will give you the work output. So, the moderator and the coolant and also this water in the outside circuit, all are water from chemical point of view, but the water which is used as the moderator inside the reactor, that is not the working medium, rather the working medium will be water, but some other body of water or some separate quantity of water which circulates only in the external circuit. So, a pressurized water reactor employs water as moderator, coolant and also working substance, but the working fluid remains separated from the moderator. Now, in order to maintain this liquid status, we have to maintain a very high pressure, and pressurized water reactor operates at a high pressure level of something like 15 or 16 megapascal. The term pressure also comes from there, or pressurized I should say. Now, at such high pressure level of 16 MPa, the saturation temperature of water will also be very high, which is somewhere around 340 to 350 degrees Celsius. Now, the water which is entering this reactor core, it is at this particular point, this water temperature is something like 290 degrees Celsius, and then the flow rate of this water is controlled such that at the exit the temperature is limited something to 320 to 325 degrees Celsius, which is well below the saturation temperature of 350 degrees Celsius. Now, if we have some idea about the energy produced in the reactor, that is Q dot, then we can always write an energy balance equation as m dot Cp into T 2 minus T 1, where m dot is the mass flow rate of this water coolant, Cp bar is the average specific heat, and T 2 is the outlet temperature at this point, whereas T 1 is at this particular point. So, if we have some idea about this Q dot and Cp being generally a known quantity, then you can control the m dot by a pump which is mounted here to keep this temperature difference, that is T 2 minus T 1, to some reasonable value of 25 to 30 degrees Celsius. And accordingly, the outlet temperature of the coolant, which is expected to be the maximum temperature, that remains well below the corresponding saturation temperature, thereby allowing single phase evaporation throughout the loop. The secondary loop, where this water which is coming from the reactor is transferring its heat, there the pressure is something like 6 megapascal only, and corresponding to that temperature, saturation temperature is around 275 degrees Celsius. So, the steam coming out through this particular point will be having a temperature around 275 degrees Celsius and a pressure of 6 megapascal. Because the temperature of water coming here and entering the steam generator is of the level of 320 degrees Celsius, a reasonable temperature difference can be obtained across the heat exchanging surfaces here. The pressure, then this steam is then taken to a Rankine cycle, which a conventional Rankine cycle which may also contain reheating or superheating and even regeneration also, but that part is external, which is similar to any conventional coal based power stations. In nuclear power plant, we only get as the operation between this 0.2 to 0.3, which is in conventional coal based power stations, the process that is done inside the boiler. But one difference with the coal based power stations to the PWRs is that the amount of energy released is much higher compared to the energy that is energy released during fission is much higher compared to the energy released during coal combustion. But the question is, how can we ensure this system pressure of 16 megapascal? Once we can ensure this high pressure, corresponding saturation temperature is already high, and therefore, by limiting the exit temperature, temperature at this point, this T 2, we can easily heat up the fluid or the steam here to any temperature of our choice. But the important part is we have to control the pressure, that 16 MPa. And for that purpose, we have a pressurizer. This is the pressurizer that we have in a pressurized water reactor. A pressurizer is connected to the hot leg. Conventionally, this leg is called the cold leg, and this one is called the hot leg, because this hot leg carries energy of much higher level. The pressurizer is connected to the hot leg, through which it is able to come in contact with the high temperature fluid. It is actually a very small pressure vessel. Its volume is very small compared to the volume of the original pressure vessel, but this small pressure vessel is partially filled with a two phase mixture, which commonly is water itself. Therefore, it can be said to be partially filled up with liquid water and water vapor mixture. We can maintain a coolant mixture temperature of 350 degrees Celsius, which automatically can balance the pressure to the targeted pressure of around 16 megapascal. Because during the saturation state, or whenever we are dealing with the saturated mixture, pressure and temperature are not independent, rather they are dependent on each other. Once one of them is fixed, the other has to be fixed. And therefore, by maintaining a certain temperature inside this, like 350 degrees Celsius, we can maintain a pressure of 60, we can maintain a pressure of the order of this 16 MPa inside this reactor. The saturation temperature also can be controlled by varying the pressure, and therefore, we can maintain a fixed pressure and temperature inside the pressurizer. Because of this two-phase nature of the fluid which is bound in this pressurizer, it is able to control the pressure inside, and also it can absorb any kind of pressure upsurge or downsurge which may appear during any operation. Now, when there is a pressure upsurge, that is, there is a very small increase in the pressure inside the actual pressure vessel, then that will cause a rise in the water level inside this pressurizer. Water, the liquid part, that being incompressible in nature, so there will not be too much change in the volume, rather the water level inside this will rise a bit, and once the water level is rising, that will result in a reduction in the volume available to the vapor phase, which is here. So, the vapor phase will get compressed a bit, and whenever the vapor phase gets compressed, we have one spray nozzle mounted here. This spray nozzle gets activated, and this spray nozzle now sprays some cold liquid water on the vapor somewhere here. The spray nozzle will put the spray somewhere here, thereby condensing some amount of vapor, and once the vapor condenses, so the pressure of this vapor part reduces accordingly. It can able to capture or retain a new equilibrium corresponding to this new position of this free surface. Similarly, whenever there is a pressure downsurge, if the pressure inside the container main reactor vessel reduces, then that will also draw a little bit of liquid out of this pressurizer, and so the pressure, there is now higher volume available for the vapor which is present, higher volume of vapor available which in this portion. So, this vapor will try to expand, but as the pressure has fallen, but both liquid and vapor part remains at the saturation temperature corresponding to the initial higher pressure. So, some liquid from this free surface will try to evaporate and occupy that portion, thereby gaining a equality or equilibrium in terms of pressure. I think I told something wrong, I would like to correct this once more. Whenever there is a pressure downsurge, there will be a reduction in the free surface level. So, the free surface say has come down here. So, now larger volume is available for the vapor phase, and hence the pressure on the liquid surface that also reduces, and because of that some liquid from this portion, as both liquid and vapor part are already at the saturation temperature. So, that will evaporate or that will flash into vapor and occupy this portions, thereby contributing more molecules to the vapor part. That increases the pressure in the vapor part, and hence is able to attain the equilibrium, or the entire system can go back to its original position. If the flushing itself is not sufficient, then we may have submerged electrical heater here. These electrical heaters also can get activated and heat up the liquid, thereby leading to some further evaporation of the droplets and getting the pressure level back to the original one. So, pressurizer serves several purposes, and the first one is the pressure control. Like I have mentioned, both pressure upsurge and downsurge can be maintained. Another function done by the pressurizer is the coolant level monitoring. Generally, the pressurizer is mounted at the top of the pressure vessel, which is likely to be the highest location of the plant, and hence if the pressurizer is having sufficient amount of liquid, then all components which are placed at a lower elevation must have sufficient amount of liquid present. Therefore, they are just by observing the coolant level inside the pressurizer, we can know the pressure of, or I should say we can ensure that there is sufficient water throughout the reactor system. And the third is over pressure protection. Somewhere here on the top of the pressurizer there will be a safety valve. if there is a certain overpressure in the system which the pressurizer is also not able to take care of, this overpressure protection valve opens, allowing some steam to escape. You can think this one, or you can to be analogous to the safety valve that we can have in a pressure cooker. Whenever the pressure inside is high, then the safety valve opens, allowing some steam to escape, and thereby gains the equilibrium back. However, if the control valve is not sufficient, or the safety valve is not sufficient, there will be another emergency protection valve on the lid of the pressure cooker. So, in case of emergency, that opens and allowing some further release of vapor phase. This overpressure protection is also somewhat similar kind. Whenever there is some excess pressure which the pressurizer is not able to handle, then this overpressure valve will open, which is connected generally to a series of pipings, finally leading to the cold body of certain fluid, generally water, and from there it can come back to the pressurized water reactor again. But during initial phase of a PW or operation, or when we are switching on a plant, then there is no vapor present inside the pressurizer. So, to increase the pressure inside the pressurizer and also inside the entire system as a whole, the gas compression is preferred. Like the pressurizer is filled with some kind of inert gas like nitrogen, and then by heating we can reach the desired pressure level, because we are controlling both the pressure and the volume of the same. So, the pressure inside the pressurizer keeps on increasing, and once we reach the desired level, we can stop this pressurization process. So, pressurizer is the most common type of reactor, and the next one in line is the boiling water reactor. A boiling water reactor is the counterpart, where again we have a big pressure vessel just like this, but inside we do not have any pressurizer kind of component here which can control the pressure, and therefore, once the heat is supplied, the liquid temperature can increase up to the saturation temperature level and may start boiling. So, in case of boiling water reactor, the liquid which enters the tank from a point, say somewhere here, or if I draw properly, it is entering the tank from somewhere here like this. It is again passes through this fuel elements, thereby getting heated up, and invariably that energy received by them is sufficient to cause them vaporize or partially vaporize at least. So, they come out of this fuel cluster as a mixture of liquid and vapor. The vapor phase is separated by some kind of separating element. We may have a separator drum also. So, it is separated from there, and the vapor phase is allowed to go out, whereas the liquid phase comes back via this circulation line. So, boiling water reactor is also a very classical design and old designs used in several countries very successfully, and the reactor rating can also vary a lot. As we do not need to suppress the boiling part, so we can operate at a lower pressure level of 7 megapascal, which allows the boiling of the coolant inside the core. Then no secondary fluid is required. Here the same fluid is acting as moderator, coolant, and also the working fluid, because the steam which is produced here, the steam inside the reactor is directly going to the turbine. After the turbine, it will pass to the condenser, and then the resultant liquid will again come back to get pumped back into the reactor, which is here, which can be viewed as something like the feed water or recirculation water. This boiling water reactor generally uses enriched uranium because of two reasons. Firstly, the water that we are using, water has little bit of absorption cross section, which may be small compared to several other isotopes, but still it can't be, but still if we use natural uranium, then we shall find it very difficult to reach the criticality, and it generally gives higher thermal efficiency compared to PWRs. Also much more safe and stable from design point of view, as we are operating in a big pressure vessel. The size of the pressure vessel being much larger, any upsurge or downsurge in the total volume flow rate can be taken care of very easily. But one big problem with the boiling water reactor is that if there is any leak in the fuel side, then the radioactive elements or the fission decay products can come into the moderator stream, and when this moderator starts boiling, then the corresponding water vapor which is going to the turbine through this line, that may also carry those radioactive isotopes. Thereby, they will making a big chance or a big probability of radioactive leakage to the external circuitry. That is one big drawback that boiling water reactor may have. That problem is not there in pressurized water reactor, because the water that is used as moderator and coolant is remaining inside the pressure vessel only, that is never going outside. This is the corresponding energy balance equation, Q dot equal to m dot into delta H, and delta H can be written in corresponding form, corresponding mixture form, where x refers to the mass fraction of the vapor phase and 1 minus x refers to the liquid fraction of the vapor phase, the mass fraction of the liquid phase. This is the complete circuitry which actually is true for both PWR and BWR. This is the reactor side, this side, and this side is the external circuit, which is essentially the same that we get in case of a coal based power stations. The steam originated either directly inside BWR or in the secondary loop associated PWR, that is supplied to a turbine, which generally is a multi-stage turbine. After expansion it goes to the condenser, and after condensation it can come back to the boiler through the feed water pump. Here another point of interest to note that the control rods in case of a boiling water is mounted below, whereas in case of PWR they are mounted from the top. As in case of boiling water, the upper part of the vessel is covered only by the vapor phase. So, there will be no point using the control rods there, rather it will be much more easier to control the reaction if they are inserted from the bottom side. Next we come to a very interesting reactor, that is called light water graphite moderated reactor, LWGR, but it is an unusual design which was conceptualized in the former Soviet Union in 1970s, and they gave a Russian name which as an acronym from generated from that is also called RBMK reactors, which as per literal translation refers to high power channel reactor. In case of light water graphite moderated reactor, as the name suggests, here the cooling medium is ordinary water, but the moderator is graphite. Like in both PWR and BWR, the same material which is water was used as both moderator and coolant, but here we are having them as separate quantities. It uses slightly enriched uranium with zircaloy cladding, and each fuel assembly is put in separate pressure tubes, like here these are each separate pressure tubes inside which we are having the fuel, and pressurized water is allowed to flow through the gaps between these fuel tubes, and thereby taking the energy produced during fission reaction. The graphite blocks are used, graphite is the moderator. So, graphite blocks are used to form some kind of structure within which these fuel assemblies are placed in tubes. And also conventionally a mixture of helium and nitrogen gas are used to enhance the heat transfer or heat conduction through the graphite blocks. This RBMK design is unique in several sense, because this is only reactor design which uses graphite and water inside this, and which itself can be a difficult combination to handle. And there are also several other issues. One big advantage that they proposes is the online fuel replenishment. As the fuels are placed in the form of separate pressure tubes, so even during running period also we can easily remove 1 or 2 tubes and we can replenish them with fresh fuels, which the advantage which was not present in case of PWRs or BWRs, because they work on pressure vessel type of concept, and everything inside the vessel needs to be stationary before doing any kind of refueling. But these are the problems with the RBMK design. One is the positive void reactivity coefficient. In the previous module, we have discussed about the void reactivity coefficient, and it has to be a negative quantity, but RBMK designs gives a positive void reactivity coefficient. The controller design was also faulty, and the design that are used in RBMK actually are the design that is used for plutonium production, but here the objective was to produce power. So, the same design can be used for both plutonium production and power, but generally the power production is the one that is the objective of a reactor, and therefore, this design corresponding to plutonium can also be a quite difficult one to handle. Actually, there out of all the nuclear accidents that has taken place throughout the world over last 3-4 decades, 3 of them are generally most well known. One is the 3 Mile Island at of US in 1979, other the very recent one at Japan in the Fukushima power stations in 2011, I guess. But the one which is associated with the largest amount of destruction is the Chernobyl power stations at that former Soviet Union, and the reactor that they had, that is actually of this RBMK style, and only following the disaster there, people started to work on the possible drawbacks of this RBMK, and accordingly they provided several kinds of modifications in the design. Like in the future design, the passive void reactivity coefficient related issues are avoided, and an attempt was made to induce the void reactivity coefficients to a positive value. But most of the RBMK based reactors are obsolete nowadays, only very few of them are working, that is also in highly modified stage. Next is the gas cooled reactors or advanced gas cooled reactors. As the name suggests, here the coolant is a gas, and invariably the moderator is graphite. So, the diagram is shown here. Again the similar to PWRs or BWRs, we are having a pressure vessel, and inside the pressure vessel the fuels are placed in the shape of rods or pellets. The gas which is passing through this reactor core, which commonly is carbon dioxide, but can also be helium, that passes through this reactor core, and once it attains a higher elevation, that is once it is the gas is made to flow over this particular steam generating tubes. Inside these generating tubes we have water which is coming from the steam generation plant, which is coming from some external source, and inside the steam generation plant that water is getting converted to vapor. Like this is where the water is entering, and here it is going out as a mixture of steam and water. The same is true for this side as well. The gas cooled reactor has a quite checkered history. The first generation of gas cooled reactors were developed at both United States, both United Kingdom and France separately. The UK based design employed magnox as the cladding, whereas the one in France that uses magnesium zirconium alloy for the cladding material. The advanced gas cooled reactor is only a modified version of the original gas cooled reactors conceptualized in United Kingdom. Commonly such gas cooled reactors involve much higher temperature, can be as high as 650 degrees Celsius. As there is they remain as a gaseous state, so there is no restriction related to the saturation temperature, and hence we can go up to very high temperature level. Then here, as already mentioned, the graphite is the moderator and CO2 is the coolant. Stainless steel cladding is used to withstand such high temperature levels, but one issue with the stainless steel is that it has a relatively high capture cross section. So, stainless steel, as it is absorbing a part of the neutrons available there, generally enriched uranium needs to be used in such AGR group of reactors. Uranium needs to be enriched to 2.5 to 3.5%. Now, the gas cooled reactors can have several kinds of modifications. There are several improved versions of these gas cooled reactors have been proposed. One of them is the high temperature reactor, which is proposed in Germany. It is actually pebblebed reactor, it is a very interesting one. Here, as you can see from the diagrams, here the fuels are shaped in the form of small pebbles, each of the diameter of about 60 millimeter. Actually, the fuel itself is may not be present into these pebbles, rather the pebbles are made of some kind of graphite based materials and also with polycarbonate and silicon carbide coating on top, and fuel is associated with, or certain amount of fuel can also be present inside each of those pebbles. The pebblebed in pebblebed reactors, the fuel is supplied continuously. These pebbles of fuels or fuel balls, they are supplied continuously, just similar to coal, how it is supplied to a conventional coal based plant. For cooling the reactor or as a coolant, helium is used, and this helium can be heated up to 700 to 950 degrees Celsius. So, here the temperature level is even higher compared to the advanced gaseous reactor, advanced gas cooled reactors, that is AGR. Next, the pressurized heavy water reactor, PHWR. This kind of reactors are also called CANDU reactors because they are originated from Canada, and the term Canadian deuterium uranium combines to this pressurized heavy water reactor. Here the most striking feature is the pressure tube type design. We have a large vessel here which is called calandria. Inside the calandria we have heavy water stored, and then the several pressure tubes are immersed into this calandria, which the tubes which are containing the fuel elements. The coolant that is allowed to pass over these pressure tubes, thereby absorbing the energy. So, the D2O is stored in the calandria, and several horizontal pressure tubes containing the fuel channels, they are also immersed into that. They also quite similar to this RBMK group of reactors, they can also be refueled at full power, allowing very efficient use of uranium. And that is why the CANDU group of reactors or the PHWR has become very popular, particularly in India. Apart from the initial PWRs, almost all Indian nuclear power stations employs PHWR kind of nuclear reactor. As we are using heavy water, it does not have any absorption cross section, or this absorption cross section is negligible. That is why we can use natural uranium, and hence the fuel cost is significantly reduced. But one problem is that the burn up is low, and therefore, fuel consumption rate also will be much larger. And another big issue, heavy water itself is very expensive, very expensive, and so whatever gain in terms of cost we get by using natural uranium, whether that is compensated or not, that we have to be careful of. And then we come to the last one is category, which is fast neutron reactor, which is truly speaking is not a thermal reactor, rather it employs fast neutron. Still, for the purpose of completeness, I am mentioning this. Here there are no moderators, because we are trying to use the fast neutrons, and as there are no moderators present, so there will be significant excess of neutrons. Moderators can itself also eat up some amount of neutrons, and that portion is not present, and also as the moderators are not going through, the neutrons are not going through any kind of scattering or slowing down process. So, they are not likely to enter the resonance absorption zone. So, there will be no resonance absorption as well. That is why fast neutron reactors have significant excess in terms of neutrons. They also requires very highly enriched fuel of the range of 10% or even more, but they, because of such high neutron excess, we generally need to have a very compact reactor core and be resulting in high power density. So, but one big problem for them, water is not suitable as a coolant because of two reasons. Common water has a little bit of capture cross sections, so it can reduce the neutron density, and also because of such large number of neutron presence, and also the fast neutron lifetime being quite small, or prompt neutron lifetimes being quite small, the rate of power production from this PHWR is very high, and that is why water is not capable of carrying that amount of energy, and we have to use some kind of highly conductive fuel that needs to be used, something like liquid metals as sodium or potassium. So, if you follow the diagram, Here this is primary sodium which is flowing through the core, and then that is getting pumped via this into the core. So, it passes through the fuels and comes out as high temperature sodium. That sodium is passing through or passing over a heat exchanger. On the other side of the heat exchanger we also have again liquid metal, and this is the secondary loop which is taking this energy towards outside to a steam generator, where this energy from this secondary loop is being transferred to water. So, we are using sodium in both primary as well as in the secondary reactor or secondary loop. So, this secondary sodium loop which can help us avoiding the radioactive effect also complicates the design and put some additional burden on fabrication point of view. In the outside loop we use water only, which gets the energy from this second sodium loop, and then in a conventional Rankine power cycle it can produce the power. Fast neutron reactors essentially employs a technique called breeding. By virtue of breeding, it can convert fertile material to fissile materials, and thereby it can produce some more fuels. That is why fast neutron reactors are also conventionally called fast breeder reactor or FBR, which is the topic of our discussion in module 8. So, it takes me to the end of this particular lecture. Here we have discussed about some of the conventional nuclear reactors like the pressurized water reactor, boiling water reactor, advanced gas cooled reactor, pressurized heavy water reactor, and also the fast neutron reactor. And as a variation of this advanced gas cooled reactor, we have also talked about the high temperature gas cooled reactor. And next lecture we shall be discussing about different generation of reactors, starting from the generation 1, where the concepts of PWRs and VWRs were proposed, and going through different generation to the modern day reactors, which are generally belonging to the generation 4, which are having several advanced categories will be briefly touched upon. So, thank you for the day.